All right, welcome back. We are now looking at the outer planets in the solar system, Uranus and Neptune. And these planets have similar features to each other. Both have a radius that's about 4 times the Earth's radius. And neither one are visible with the naked eye. So in other words, you need a telescope to see either Uranus or Neptune. Now we can pan up to the data projector and we see how much bigger Uranus and Neptune are in relationship to the Earth. When you work this out carefully, you find that these outer planets are 4 times the radius of the Earth. And so because the volume goes like the 3rd power of the radius, this means that we have 64 times the volume of the Earth in either Uranus or Neptune. Now these planets, because they were not visible without a telescope, we didn't really know where to look for them. And so the way that this was first deduced was by looking at Saturn's orbit carefully and noticing that there were wobbles in Saturn's orbit that could not be accounted for by the combined gravitational effects of all of the planets that were closer in than Saturn. And so it's deduced then that there must be another planet that's periodically pulling on Saturn that's giving rise to these wobbles. And so they looked then in the location where they felt that that object should be, and there it was, Uranus. The problem, though, of course, with this is that their mathematics was wrong. And so they just found it by blind, stupid luck. But still, it was the impetus for looking in that particular part of the sky to find the planet Uranus. And so that was found in the 1700s. But then once Uranus's orbit was tracked more carefully, we discovered that there were also wobbles in the Uranian orbit, which gave rise to a prediction as to where Neptune should be located. And so Neptune then was found something like 100 years later in this more distant orbit from the Sun. Now Uranus's distance from the Sun is about 20 astronomical units, and Neptune's distance is roughly 30 astronomical units. The period of orbit for Uranus is something like 84 Earth years. And for Neptune, it's about 165 Earth years. So this is in agreement with Kepler's 3rd law of planetary motion for the relationship between the distance of the planet from the Sun and the period of its orbit. For both of them, the rotation period is something like 16 to 24 hours. So they're spinning pretty fast. Now, when we look at Uranus, what we often would like to try to remember is, what is it known for? What is something that would be the most spectacular thing that we could use to differentiate it from the other planets? So these are the kinds of questions I could ask on an exam, say as a set of matching questions. And so Uranus is remembered as the planet that got knocked on its side. And by this we mean that it's got a steep inclination of its orbit relative to the ecliptic plane. So here is Uranus, and then way out here somewhere is the Sun. And we'd expect then that if this is the ecliptic plane, which is a plane that comes out parallel to the floor, that the rotational axis would be vertical, but no, it's not. It is inclined all the way at a 97-degree angle to the vertical. Okay, so it's spinning fairly rapidly. 16 to 24 hours is the period of its day, but with a highly inclined rotational axis. So something came along and hit Uranus, an oblique collision, maybe an Earth-sized object, and turned that rotational axis, we believe, all the way over, pretty much on its side. So we can see this a little better with the data projector pictures. So because it's been inclined at more than a 90-degree angle, sometimes the sun will be pointed straight at the South Pole. Other times during the Uranian year, it'll be pointed straight at the equator, which means the sun would be directly above the equator. And then at other times, you would have summer at the North Pole. But we also have to remember here that the sun is a very distant object and would probably not look much bigger than a glorified star. It's at 20 times the Earth's distance from the sun, which means we're only getting 1/400th the light. And so the sun wouldn't be something that you could really warm your hands by. It would still be freezing cold. We're looking at temperatures on the surface of perhaps minus 300 degrees Fahrenheit. So we might wonder, though, why is it that the axis being inclined like this is evidence for the planet being hit by an Earth-sized object and not just an instability in the orbit that caused it to be oriented like that? And the answer is because the moons of Uranus are all in a plane that's perpendicular to the rotational axis. So here's the moon plane. Here's the rotational axis. And so what this is an indication of is that there was a huge collision that happened, threw material out, which then flattened out as the uranium system started to condense out of this swirling ball of gas and dust. Eventually it flattened out, became a mini solar system with the moons oriented perpendicular to the rotational axis. So this is an indication then that the rotational axis hasn't changed its direction over geologic time, but rather has been fixed in that position, and the orientation of this little mini solar system, which is all of these moons going around Uranus, is at a highly inclined angle. All right, so we have many different moons for the Uranian system, but the one that I'm most interested in you knowing something about is Miranda. And I'll show you a picture. If you look again up at the data projector, we can see some of the different moons of Uranus in scaled comparison to the size of Earth's moon. And then we'll notice that Miranda is that little tiny moon that's kind of in a clockwise direction all the way around. So why would we be so interested in that moon? Well, because that moon has so many interesting features associated with it. So if we blow up that picture of Miranda, we see that it isn't totally spherical in its shape. It's got deep grooves in the surface, and it's only about 100 miles across. And so somebody that was trying to explore that moon it would be like a geologist's field day. They would have so much fun checking out all of the different little irregular aspects to Miranda. And so there is some interesting science that goes along with this. We think that Miranda was probably knocked apart by a huge collision. So here again is evidence for a big collision. We have Uranus getting knocked on its side, and then Miranda, we believe, was knocked apart by early collisions when the solar system was first forming, but then partly came back together again. Some of the pieces probably just kept moving away, and that's the reason why Miranda is so much smaller than those other moons. That the pieces that remained came back together, but didn't have enough heat to generate a perfectly spherical shape. And so why would an object want to be a sphere? Well, because you have to have equal pressure, equal gravitational force generating equal pressure pushing in from all directions. But because Miranda is maybe only 100 miles across, there wasn't enough gravitational force to melt the moon enough so that all of those rocky pieces could work their way back into a perfect sphere. And so on the surface, what we end up with is this only 100 miles across, but you have a deep canyon that is something like 13 miles deep, and it's only 100 miles across. So this is way, way deeper than the Grand Canyon. And so you could imagine trying to explore this. There'd be very low gravity on the surface. And so let's say you get to this 13-mile deep canyon, and you start doing a little climbing here. You're not too worried about it because the gravity is small, and so you can jump pretty far distances, and so you're not really figuring that this is going to cause a problem. But then, just kind of without really paying enough attention, you accidentally lose your grip with the side of the cliff face, and you start to fall. Okay, so at first you're not too worried. After maybe 5 minutes or so, you'd only be going maybe 5, still 10 miles an hour at the most. But as you continue to fall, it would take you something like 35 minutes to get to the bottom. And by that time, you'd be really moving fast. You'd be going maybe 100 miles an hour. And then that would cause major damage when you hit the bottom. And so normally, when somebody falls off a steep cliff, you hear a big scream, wow, it's over in just a second or two. But if you fell off of this cliff on Miranda, you would have 30 minutes to think about it before you hit the bottom. And so it would be advisable to watch your step whenever you're exploring one of these objects, even if at first you wouldn't be going that fast. Eventually, you'd have to figure out a way to grab a hold of something before your speed picked up and you got going too fast. Now, because Uranus has experienced such a big collision, it has very few interesting surface features. And we think these surface features usually are the result of heat escaping from the interior of the planet. But the collisions, we think, upset the internal heat dynamics. We don't know exactly what happened, but we do know it got hit, and it's the only planet in the outer solar system that isn't radiating as much heat as it absorbs from the sun. So that means that there's not that normal source of gravitational contraction generating heat. And then that heat, as it escapes to the surface, is what would create the interesting surface features. And so the collision that knocked Uranus on its side upset the internal heat dynamics. And so Uranus then releases less heat than it absorbs from the sun. Which isn't that much. It doesn't absorb that much either. Remember that if it's at 20 astronomical units away, that we're looking at only 1/400th the amount of solar intensity, because it goes like 1/20 squared. It's 20 times farther away. It's an inverse square law for light as well as for gravity. Okay, and so this then makes the surface of Uranus kind of boring looking. And let me just see if I can find a picture of that for you here. Yeah, looking at this first picture, we can see how uneventful looking the surface of Uranus is. And so when the first robot explorers went to the outer solar system, they looked at this boring surface and they immediately turned their attention to the moons. Neptune, on the other hand, has a lot of high velocity winds, and at one time at least had a storm that was as big as the Earth. So if we look for a second at Neptune, here in this next picture, we see, look at that. We see some kind of streaky clouds and then a gigantic cyclone, it's believed, that is called the Great Dark Spot. Okay, so the interesting thing about Neptune, too, is that Neptune is farther away than Uranus. And yet, it is at about the same temperature. Why? Well, because of more atmosphere holding in heat. That's a greenhouse effect. And so both Uranus and Neptune are at about minus 300 degrees Fahrenheit. But Neptune, because it's able to hold in more heat than Uranus at a greater distance away from the sun, gives rise to about the same surface temperature. So as we look at these different features on Neptune, we see that there are a couple of things we can remember for Neptune that are important. One is that it has the fastest winds in the solar system. Something like 1,300 miles per hour, which is roughly double the speed of sound on the Earth. And it had that great dark spot. Which looks like a huge cyclone. About the size of the Earth. And so a lot of people, when they first saw that, believed that that might be like the Great Red Spot on Jupiter, a cyclone that could have been around for hundreds of years and might be stable. But as we got more data and started looking at Neptune again, when the Hubble Space Telescope came online in 1995, the Hubble Space Telescope did not see the gray dark spot. So this was a great disappointment to many scientists, because this happened in 1995, whereas the picture that you saw there was 1989. This is when the Voyager space probe went by and the great red spot was observed, or the great dark spot, sorry. And so it was gone in just 6 years. And so what happened? Well, Neptune doesn't appear to have the same kinds of zones and belts that Jupiter does. And remember, it was the stability of the gray-red spot happened when you had oppositely directed winds that were moving at hundreds of miles an hour, and then that kept the vortex moving at the junction between those. Whereas here, we don't seem to have that same kind of a structure. And so the cyclones are less stable, just like on Earth. But Neptune does have other very small cyclones, and so it does appear as though these cyclonic features do appear every now and then on Neptune. Now there's one moon of Neptune, which we can look at again up on the data projector, and that's Triton. So here, now not Titan, don't confuse it with Titan. This is Triton. Remember, Neptune is a kind of a Roman god of the water, and Triton has the big pitchfork, and so they tend to pair them up like that. And so you can remember that when you think about Triton going around Neptune. And so here we see some, this is actually debris that has fallen out on the surface from nitrogen geysers. So this is an interesting aspect then to Triton, which is this moon of Neptune. That's the only moon that you need to know about for the quiz and exam. It's about the size of Pluto. And it goes around Neptune in the wrong direction. Remember that we said before that moons tend to go around their parent planets in a counterclockwise direction, most of them at least, but not Triton goes around in a clockwise direction. What does that tell us? Well, it tells us that Triton was probably captured by Neptune and didn't form along with Neptune in the early solar system. It might have been like Pluto. It might have been a dwarf planet that was captured by Neptune's gravity. And it could have even been a close interaction with Pluto that could have caused this to happen. Because Pluto is another large object that's in that same general vicinity. But moons that go around their planets in a clockwise direction, in contrast to our moon, which is getting farther away from the Earth, going in a counterclockwise direction. This clockwise motion is going to cause Triton to get closer and spiral in to Neptune eventually. So we'll have a collision in the future. And it'll probably be torn apart before it ever hits Neptune by going inside the Roche limit. Once it does that, then it'll be torn to shreds and all of the pieces will come raining down on Neptune. And so we don't know how long this will take to happen, but when it does happen, it'll undoubtedly be a very spectacular sight. Now, one thing that we can remember about Triton is that it has the coldest known surface. At minus 400 degrees Fahrenheit, 400 degrees below zero, is cold enough to take the air that we breathe and freeze it. And so that is essentially what happens on the surface is we have frozen nitrogen. But because of the tidal friction that is happening, as Triton spirals in toward Neptune, as it gets closer to Neptune, Triton, as it goes around in this clockwise direction, is being pulled on harder by Neptune on the near side than the far side, and so that's creating heating. And that heating from tidal friction, even at minus 400 degrees, is heated to the point to where we get nitrogen geysers. So even with an object that is at such a low temperature, we can still have some dynamic effects taking place in which you have solid nitrogen turning straight into a kind of a liquid geyser of liquid nitrogen shooting out from the surface. And so this is an indication of how different these outer worlds can be in our solar system.